Well, thank you, Anne, for that kind introduction. Ladies and gentlemen, good morning. 2 more minutes. It's great for me to be back here in Sydney Opera House. It's also great for me to catch up with my colleague Lawrence Krauss. We have adjacent offices at Arizona State University, but we both travel so much that we're not often there together. So it's nice to be in the same place for once. Now, a pivotal event in the history of science occurred in the year 1859 with the publication by Charles Darwin of his famous book, The Origin of Species. And in this book, Darwin gave a convincing account of how, over billions of years, life on Earth had evolved from simple microbes to the richness and complexity of the biosphere that we see today. But he pointedly left out of account how life got going in the first place. It is mere rubbish, he said, thinking at present of the origin of life. One might as well think of the origin of matter. Well, I'm pleased to say that we physicists have now explained the origin of matter. Lawrence mentioned that. And the question is, how are we getting on explaining the origin of life? Well, I have to say that a century and a half later, we're still largely in the dark about life's origin. Now, the problem of life's origin is really 3 problems rolled into one. There's the when, the where, and the how. And I'll talk about each of these in turn. First of all, when did life begin? Now, we can't say exactly when it began, but what we can do is trace the fossil record back in time to the earliest point where we can be fairly sure. That is, we look for the oldest traces of life on Earth. And it turns out that those oldest traces are found right here in Australia. Well, not quite here, but on the other side of Australia, in the Pilbara region. That's near Port Hedland. And in that region, there are rocks that are sticking out of the hillside, which are 3.5 billion years old. So they're among the oldest known rocks on Earth. And those rocks contain what is probably the oldest traces of life on Earth that are generally agreed. There's some dispute. There are rocks a bit older than that, but there's some dispute about whether the traces of life are genuine. But those particular rocks, we're pretty much agreed, do contain evidence for life. But this evidence is in an indirect form. So I took the trouble to go there back in my moustache days, and it's best not to go in the summer. It's actually very hot in that part of Australia. And this is what the scientists get excited about. This rock here, it's called chert. And if you look carefully in that chert, what you see are these little features. They're like ice cream cones nested together and sliced through. Now, I have to say that doesn't look very exciting to me, but the astrobiologists, they're the people who study life in the universe, they get very excited by these features, which have the name stromatolites. Now, actually, technically, they're not stromatolites, they're fossilized stromatolites, 3.5 billion year old structures. And they're not themselves, were never themselves living things. They're fossils of microbial mats, so microbes that deposited sediment in layers over many thousands of years, and then these things became fossilized and embedded in the rocks, and that's what gets them excited. Now, you might say, well, show me a living stromatolite. They're very rare. It's hard to find stromatolites, but you can, if you're visiting the Pilbara region, I do recommend it. Then a couple of days' drive from there, you go to Shark Bay, and there you see living stromatolites. And you see, what I like to say is, if you imagine getting in a time machine and going back 3.5 billion years on Earth, this is as good as it gets. You know, this is life on Earth. That's about all you see. It's really, really boring. So it took a long time for life on Earth to evolve the complex structures like us. In fact, for about 2 billion years, there wasn't much to see. And so it's not very exciting, but it's tremendously significant that we see fossils of structures like this in these very ancient rocks. So it looks like life was established on Earth quite firmly 3.5 billion years ago. Now, let's put that into context. The Earth itself, the solar system indeed, is little over 4.5 billion years old, and of course it didn't form overnight. The planets formed from a swirling disk of gas and dust around the proto-sun, and it took really quite some hundreds of millions of years for this process to be completed. And during that time, huge chunks of material rained down on the newly formed planets. So this is a NASA depiction of this process, and here's another one, and we can imagine the early Earth being bombarded ferociously, in fact all the early planets bombarded ferociously by huge comets and asteroids and rocky bodies. Now, I'm sure everyone's familiar with the fact that the dinosaurs were probably done in by a comet that smashed into Earth about 65 million years ago and created a crater about 180 kilometers across in what is now northern Mexico. Well, that was small-scale stuff compared to what was going on in the early time in the solar system. The biggest of these impactors would have had enough energy to boil the oceans dry and swathe our planet with incandescent rock vapor. And so this is an artist's depiction of this sort of hell on Earth that would have persisted. It's a little hard to know, but certainly for some hundreds of millions of years. And in fact, the best record of this early bombardment comes not from Earth itself, because the material gets reprocessed, but from the Moon. And on the Moon, all those craters that are so familiar tell us something about the early heavy bombardment. And if you plot some sort of schematic graph, what you find is that this bombardment abated round about 3.8 billion years ago, whereas, as I've told you, life on Earth extends back through 3.5. Of course, it didn't appear overnight, so presumably back to at least 3.6 billion years ago. And so this is a very narrow window. In fact, Carl Sagan, many years ago, said that life must be easy to get going because no sooner was Earth ready for it than up it popped. Turns out that that argument is fallacious. It might be right, but it doesn't have to be. So I'll come back to that. But the important point is that there's been life on Earth for almost the entire duration of when Earth has been habitable. Okay, let me come on to the where part. Where exactly did life start? Well, I mentioned that Darwin wouldn't be drawn on the subject of life's origin, but in a letter to a friend, he did speculate about what he called a warm little pond, over which, over many millions of years, chemicals might leach out of the rocks, and by some sort of process of chemical self-assembly, more and more complex molecules might form until eventually something would crawl out of this warm little pond. And that's as far as he would be drawn. But it did give rise to the popular notion of some sort of primordial soup, at least an aqueous medium in which some sort of chemical magic might take place. But we don't quite know what that magic is. So is this warm little pond idea a viable one? Really, I have to say that it's not. Remember this hell on Earth, so this early bombardment would have meant that warm little ponds wouldn't really have survived for very long. And so the attention in recent years has shifted from ponds to what is sometimes called the deep, hot biosphere. Now, it comes as a surprise to people that life on Earth is not just restricted to its surface. In fact, a substantial fraction of the Earth's biomass is actually living inside the Earth, not on the surface. Deep down, nobody quite knows how low you can go, but it's certainly some kilometers. And of course, the organisms that live inside the rocks deep down are microbes, and they live in the pores of the rocks. And this is not a very congenial place to be. For a start, what do they do for sustenance? Basically, they have to make do with what's there. And to be honest, it's not so much that the rock, though the minerals are useful for other purposes, but there is stuff coming up out of the Earth, like hydrogen and hydrogen sulfide, that acts as the fuel for this primitive metabolism in these microbes. And they're still there. They're still down. If you could drill down under our feet for some kilometers, you would find it's teeming with life down below us. And that seems a safer place to be. If the Earth is being bombarded, you don't really want to be anywhere near the surface. And some evidence that life started inside the Earth, not on the surface of the Earth, comes from these hot springs, the base of the ocean, where the lava hits the water. Basically, there are regions where the Earth's plates are moving apart and stuff is coming up from deep down. And this hot material, when it meets the water circulates and reaches temperatures of up to 350 degrees Celsius, squirting out of those jets. They're often called black smokers because they make black chimneys on account of the minerals that they deposit. And what came as a great surprise to biologists about 35 years ago was the discovery that this region around these black smokers is home to a rich ecosystem, a vast range of microorganisms making a living at temperatures above the normal boiling point of water. The water doesn't boil because of the high pressures there. So making a living at temperatures above the normal boiling point of water, and they can support an entire food chain with invasive species like crabs and tube worms. And now, the significant thing is when you sequence the genomes of the microbes at the base of this food chain, you find that they're among the oldest and deepest branches on the tree of life. You can sort of reconstruct a tree of life from all the species and work backwards and see which organisms have, as it were, changed least over the billions of years on Earth. And it turns out to be these critters that live in these hot spring areas. And also, I think, in my view, the surface around these hot springs, although it's deep under the ocean, is still a hazardous place. And it would be more likely that life would form even deeper than that inside the Earth. But having said all that, all I've told you is that life established itself on Earth by 3.5 billion years ago. But we don't actually know that life on Earth started on Earth. It might, for example, have come from Mars. How could life form on Mars and then come to Earth? How is that possible? The next slide says it all. That same bombardment, which pulverized the surface of Earth, Mars, and all the other planets in the early days, also served to propel material around the solar system. If Mars takes a hit, even today, by a comet, say 10 kilometers across, that will splash huge amounts of material into solar orbit, and some of that material comes to Earth. And it comes as a surprise to people to learn that there are Mars rocks right here on Earth. But there are. Here's a picture of me holding one. Now, I have to say, it's a bit of a story to this. This picture, this rock, was collected by Douglas Mawson, unrecognized for what it is, as a piece of Mars. And it was in the geology department museum at the University of Adelaide for years and years until it was recognized as being of Martian origin. It actually fell in Egypt some decades ago and apparently killed a dog. And I think that's the only known canine fatality from a cosmic object. But in the early days, they were quite relaxed about this rock, and they used to lend it to me, and I would take it to lectures and even travel around the world with it once, and would often, it was in my pocket, would often forget about it, but it was always a great topic of conversation in pubs. You'd say, oh, it's my round, lads. Oh, look, this is a piece of Mars, and people would be skeptical and consternation and so on, but it was always a great thing to have with me. But now, of course, they realize it's worth millions of dollars. They don't let it out. But at Arizona State University, we have not one, not two, but 3 Mars rocks. Somebody can ask later on, how do we know they came from Mars? I won't get into that. Anyway, the question of rocks from Mars was propelled to public fame by none other than Bill Clinton. I call this the rock that made Bill Clinton famous. Because he stood on the White House lawn in 1996 and proclaimed that NASA had evidence for life on Mars in the form of this Martian meteorite that was found in Antarctica that contained these funny little features that for a while looked to be like fossilized Martians, albeit diminutive. Since then, the evidence has largely gone away, and I think very few people still feel that this particular meteorite contains evidence for life on Mars. But, it's an interesting thought. If there was or is life on Mars, we might detect traces of it in Mars rocks right here on Earth. So that's an interesting aspect. Okay, so much for the where. Let me move on to the how part. And this is the really tough part of the problem of life's origin. How did life begin? And I think I can be quite upfront about this. We haven't a clue. I mean, we really do not know. And it's sort of depressing to think we may never know. We may never have a blow-by-blow account of how life on Earth got started. And part of the reason for that is it all happened such a long time ago. So even if life on Earth started on Earth, all traces of the early processes will have been obliterated a long time ago. However, I think we would settle for something less than understanding each step of the process. We would be content to know simply, was it a bizarre fluke, maybe unique in the observable universe, or is it a chemical inevitability? That is it bound to happen given enough time? Now, during my career, it's been very curious. The pendulum has swung quite decisively. I got interested in searching for life beyond Earth, and in particular searching for intelligent life beyond Earth, aliens. I'll come to that in a moment. Back in when I was a student in the 1960s, one might as well have professed an interest in searching for fairies. It was widely assumed among all the sciences that life on Earth was a bizarre fluke unique to our planet. And no person said it better than Jacques Monod. He said, "Man at last knows that he is alone in the unfeeling immensity of the universe, out of which he emerged only by chance." That was in 1970. Well, I have to say, this did coincide with a period of Gallic nihilism, and he looks suitably miserable about this pronouncement. And you might say, well, that was just his philosophy. But Francis Crick, Mr. DNA, had a similar opinion, and in 1973 wrote Life Seems Almost a Miracle, so many of the conditions necessary for it to get going. Well, we scientists don't believe in miracles, so we've got to do better than that. And so that idea that life is a sort of a fluke, we are freaks, it's a bizarre aberration in the universe, that feeling seems to have changed. And so in more recent years, there have been much more upbeat comments. So here's one by Christian de Duve, a Nobel Prize-winning biologist, just like Francis Crick, drawing a very different conclusion. He says life is almost bound to arise wherever physical conditions are similar to those of the Earth. That was in 1995. And he's got this wonderful phrase that life is a cosmic imperative. And so the question is, what is the case? Is life a bizarre fluke, or is it a cosmic imperative? I get infuriated because very often get asked by journalists, how likely is it that we will discover life out there beyond Earth? And I say, the question is meaningless, and it's meaningless for a very simple reason that many of my distinguished scientific colleagues seem to forget about. Okay? How did life begin? If we don't know the process that transformed non-life into life, we can't possibly estimate the odds of it happening. You cannot put the betting odds on a process that you don't know. If you know the process, even if you can guess the process, you can have a stab at figuring out how likely it is. But as we don't know what that process was, we absolutely haven't a clue. We can say nothing whatever about the likelihood of life starting, which is the same as the likelihood of life beyond Earth. Absolutely nothing. Now, there's no lack of real estate on which life may have arisen. And so this is a satellite, Kepler, now sadly not operating correctly. It's been up there in space. It's a NASA mission, and it's been looking for extrasolar planets, that is, planets going around other stars. When I was a student, nobody could be sure there were any planets going around other stars. Now there's a catalogue of hundreds, if not a couple of thousand, of candidate objects. And these objects, the planets tend to be, on the whole, much larger than Earth, but the Holy Grail is to discover Earth-like planets going around sun-like stars. And the statistics of this process are now good enough that one can have an estimate of how many Earth-like planets, depending a little bit on how you define Earth-like, how many Earth-like planets there are in the galaxy. And this is a typical report. You'll be very familiar with this sort of thing. I'm sure any of you who are following science will have picked up this, in my view, ludicrously upbeat assessment of the likelihood of life beyond Earth. So billions of Earth-like planets in our galaxy. And the key word here, you see billions or tens of billions, in this case, of habitable planets. And people think, oh, tens of billions of planets with life. What they forget is that habitable does not mean inhabited. They sound the same, but they're very, very different. Just because a planet could sustain life of the form we have here on Earth doesn't mean it's going to have it. A habitable planet becomes an inhabited planet if and only if the probability of non-life turning into life is quite high, is not incredibly small. But we don't know that because we don't know what the process was. So let me just stress that point. If there's any take-home message from this lecture, it is that we do not know how non-life turned into life, so we can't estimate the odds. Now, we can hope, if like me, interested in the idea of life beyond Earth since being a teenager, if you feel like me, then you will hope that there is a fast-track pathway from non-life to life. You may hope that there's a life principle in the universe, a sort of law of nature that says, given the matter, given an energy source, given enough time, then life will out. You may hope there is such a principle. I hope there's such a principle. But we haven't yet discovered it. There is no known such principle in physics or chemistry. We haven't found a life principle. We could believe it as an act of faith that it might be there, but we haven't found it. So we must contend with the fact that it could be that life is restricted to Earth. Maybe it's splashed around a bit in the solar system, but it could be that we're unique. And that's the philosophical conclusions of that are very deep. But let's go with the idea that the nicer idea, in my view, that it is much more probable. So I think we're all agreed that somehow a chemical mixture transforms itself into life. So how can we make progress on that mysterious process that we don't know? Well, the first thing is we could ask a chemist, of course. Seems like the obvious thing to do. Could a chemist cook up life in the lab and show us how it can be done? Well, the first attempt to do this was made in a famous experiment by Stanley Miller under the guidance of Harold Urey way back in 1952. And what they did was to take the components of what they thought the Earth's early atmosphere was like and put it in a flask there and sparked electricity through it for a week. And a sort of brown sludge appeared in this flask. And when they analyzed the sludge, they found to their delight it contained amino acids. Now, amino acids are the building blocks of proteins. And so you might think, well, that's one step on the road to life, one small step. And that was the prevailing view in the 1950s. Well, you know, if Miller and Urey could get amino acids in a week, imagine if they could get funding to run the process for 1 million years. You know, maybe it would just be a road, a pathway down which a chemical mixture would be inexorably conveyed by the passage of time with life as the destination, just more of the same. That early optimism has gone away, partly because of thermodynamics. It's dead easy to make amino acids. In fact, you find them in meteorites. You don't need very special conditions. It's because it's what we call thermodynamically downhill. It's favored, whereas the next steps of the process, assembling the amino acids into peptide chains, is an uphill process. It goes against the thermodynamic gradient. And amino acids are only one part of the whole story. We also need nucleic acids and a whole bunch of other things. And really making those things in the lab turns out to be really, really difficult. But part of the problem is, of course, what we don't want in the origin of life story is anything like an intelligent designer. And the people who call themselves synthetic biologists, or in the Miller-Urey experiment, they set out trying to design an experiment to make life. So even if we could do it in the lab, even if with enough funding we could one day make life, that still wouldn't convince me that nature would know how to do it without having a plan in advance, without being intelligently designed, which I don't think it is. So that's one problem. The other problem is, look at this picture. This is a picture of what is called intermediary metabolism. These are the pathways in a modern cell, only a small part of this. And in the trade, these things are known as reticulograms for obvious reasons, almost approaching the complexity of the London Underground map. And so biology is very complex. And so the question is, if you're just accounting for making the building blocks, what about assembling all those building blocks into something much more complex like this? So it's a little bit like saying we've cracked the problem of how the Empire State Building came to exist. We've discovered how to make a brick. So the rest must just be more of the same. So it's not how to make the building blocks, it's how to assemble them into these very specific, very elaborate, complex structures. But there's actually a more fundamental problem running through all this. It's really a philosophical problem, and it's one that preoccupies me in my own research in this field. And that is the problem best asked, what is life? And so that's something that scientists like to do again and again and makes great coffee time conversation, goes on and on and on. But basically, if you talk to a physicist or a chemist, what is life, you'll be told a story in terms of things like matter and force and molecules and energy and entropy and all that sort of stuff. And a lot of it's been worked out. And so that's the narrative you get. If you go to a biology department, ask a biologist what is life, you'll be told a story in terms of coding and signals and instructions and translation and transcription, all those sorts of things. In other words, information speak. So we have two complementary descriptions of what life is. One is it's all about molecules and shapes and chemical affinities, and the other is it's all about information processing. And you might think, well, how can we have chemistry and physics departments and biology departments in the same university? These people are talking conflicting languages. And they say, no, these are complementary descriptions of the same phenomenon. And that's well and good, so long as you're discussing the phenomenon as we find it. But the problem about life's origin is that then we're talking about the physics and chemistry transforming into the biology. We're talking about matter and force and so on turning into information processing. If you like, put crudely, we're talking about stuff turning into bits, informational bits. How does stuff become bits? How? Because in physics, the stuff calls the shots. Cause and effect are framed in terms of particles and forces and interactions. In biology, causality is framed in terms of signals and information. How did matter bestow upon information that type of causal efficacy? It's a very deep problem. There's an analogy, which I think you'll appreciate, and that is with computing. So here's a screenshot of my computer a couple of years ago. And this is my beautiful wife, Pauline, here, and we've just been to the Taj Mahal, all very romantic. And then there's some other stuff, less romantic there. But, to me, if I just had never seen a computer before, Windows would seem like a miracle. Just remember, crick, seems almost a miracle. Explain it to me. So if I go to a computer science department and say, explain Windows to me, and if the scientist took the back off the computer and said, look, I can explain it. We've got some silicon in here, and there's some copper, and then there's some iron. And, we notice with the silicon, if you look very carefully, there's these sorts of patterns inside. And we're not completely sure of all the details yet, but we think it's got something to do with those patterns. And, we're hot on the trail, and we will be able to explain all of Windows very soon in terms of this. Well, you wouldn't be very impressed, because what you're getting here is a story about the hardware of Windows. And that's fine. I'm not denigrating the people who work on computer hardware. Where would we be without them? But in the origin of life field, the hardware, the chemistry, corresponds to the hardware. It's the stuff of life, the substrate in which life's magic is instantiated. What we're really interested in, what I'm really interested in, is the software of life. So for 100 years, the origin of life field has been dominated by chemists looking for the hardware, and that's fine, let them get on with it, but they haven't made a lot of progress. In recent years, we've started asking about what about the software? What about the information processing capabilities? How do we make progress with that? Well, maybe you ask a computer scientist, a famous founder of computation, John von Neumann. He and Alan Turing together, responsible for the modern electronic computer. And von Neumann was very impressed by the analogy between what is often called a Turing machine, a universal computer, a machine that could compute anything that was computable in one machine, a universal general-purpose machine, with the notion of a universal constructor, a system that could construct, according to a program, anything you asked it to construct, including itself. So it would be a self-replicating machine. And von Neumann wrote papers and a book about the concept of asking the question, is it possible to build a machine that could construct any physical system, including itself? And so he laid down the logical architecture of what such a machine would be. And this was before the unraveling of the genetic code and DNA and all that stuff. Turns out that life as we know it is actually very much like a von Neumann self-replicating machine. But needless to say, we haven't made any such machine ab initio, although some people think that 3D printing is getting rather close to a von Neumann machine. But basically, we don't fully understand the software principles. We understand a bit about the hardware, don't understand very much about the software, but in my personal opinion, advances in understanding life's origin will come from a better understanding of the complex web of information processing going on inside organisms and how that may have emerged from information processing in primitive chemical networks. So that's where I think the future lies. But mostly we haven't got there yet, so this is a list of questions before I go on to the final part of the talk. How did it all start? How did software emerge from hardware? How did bits come out of stuff? We don't know. How did non-trivial programmable construction, because it's not, so a living organism just doesn't make any old thing, it makes a very, very specific thing according to instructions contained in the DNA. How did that type of programmable and importantly reprogrammable, because that's how you get evolution, life gets reprogrammed to produce something different. How did reprogrammable construction emerge just from dumb molecules just banging around and interacting with each other? How did digital information storage emerge? So we're all convinced of the power of digital information processing. I'm old enough to remember the slide rule. That's called an analog computer. So slide rules, you whipped out of your pocket and did the calculation like this. These days, we think, no, that's really very inefficient. We use digital computation, and now we have digital radio, digital television, digital everything. And that's because it's a very, very efficient way of doing things. Well, life went digital 3.5 billion years ago with life. How did it do that? How did it go from storing information just in things like chemical gradients to storing it in these digital units like nucleotides in DNA and the codons and so forth? I won't get into. And then it's all very well to have digital information processing going on, but it's got to do something. It's got to be useful. If you sequence a molecule of DNA, it's just a sequence. You can't tell by looking whether it's junk or whether it's something that's going to code for a biologically functional protein. There's nothing in the sequence itself. Nature is blind to such sequences. It's only in the context of the entire milieu, and that may mean much more than just the microenvironment of the cell. It could mean the microenvironment of the organism. It's only in that context we can say that we have biologically functional or useful information. How did that concept of the global environment having some sort of, I would still say, causal efficacy over what's going on at the molecular level, how did that happen? And let me repeat the answer. We haven't a clue. I mean, we really are in the dark. We've got some great ideas, and I have some colleagues doing great work investigating this stuff, but it's at the level of toy models. We really feel that we'd like to understand if there is a life principle. We think it's in the field of complexity science and software and information processing, that's where we would discover it. And we'd like to know if there is such a principle. Is it general across a wide range of complex systems, or is there something specific about the carbon? Okay, so given that we're really stuck, how can we test the hypothesis that life starts easily? Is there some way we can just go and find out? There is one way, it turns out, and that is we look for a second genesis of life, life 2, if you like. If we can find that life has started more than once, well then, independently, more than once, well then it does look like it's pretty easy to happen. Well, what is the most Earth-like planet that we know where we might go to look for life 2? Would it be Mars? Would it be an extrasolar planet? No, the most Earth-like planet we know is Earth itself. If it's the case, as Christian Davies thinks, that life pops up readily in Earth-like conditions, it's a cosmic imperative, then surely it should have happened more than once right here on Earth. Well, how do we know it didn't? How do we know all life on Earth is the same life? Has anybody taken the trouble to look? Well, it turns out that until my colleagues and I raised the awareness of this issue some years ago, nobody had really even thought about it. But it could be, I should say, that most life on Earth is microbial life, and most microbial life hasn't been characterized, let alone sequenced and cultured in the lab. So most of that life is mysterious. How do we know it's all the same life? You've got to delve into its biochemical innards. You can't tell by looking whether it's the same life as us or some other type of life. So it could be that there is truly alien life under our noses, or even in our noses. So, if life on Earth started more than once, we're talking not so much about another branch on the tree of life, but another entire tree, 2 trees of life. How might that have happened here on Earth? Well, I told you about the cosmic bombardment. So imagine that the life got going, say 4 billion years ago, then along came an impactor, wham, and blasted a lot of material off, sterilized the planet, and then things cooled down, and then life too got going. But then a few million years later, some of that material with life 1 cocooned inside it, came back again, then you'd now have 2 forms of life on Earth, life 1 and life 2. And this could have gone on again and again. So the conclusion is that we sometimes call this a shadow biosphere. If Earth has, or once had, a shadow biosphere, we could conclude it does start readily, and therefore it will be widespread in the universe. We could conclude that life will be a fundamental, and therefore a significant cosmological phenomenon, and not just a trivial local aberration. And we wouldn't then be the freaks I've been talking about. We would actually feel at home in the universe. And I'm going to finish by just touching on the subject that I think fascinates everybody about life in the universe, why we want to know the answer to this question, and that is the question, are we alone in the universe? Is there anybody out there? So this is the subject of SETI, the Search for Extraterrestrial Intelligence. And I should just mention in passing that for some years I've been the chair of the SETI Post-Detection Task Group. So it's our job to deliberate on what happens if ET calls. You can ask me about that in question time. But at this stage, of course, we don't know there's any life out there, let alone intelligent life. But the way people search for it is using radio telescopes, like this one at Parkes in New South Wales, very famous. There's even a dedicated system called the Allen Telescope Array, which was partially paid for by Paul Allen, but has now run out of money. And so it's been sort of hibernated. The plan is to have some hundreds of dishes like this, dedicated to just looking to see, sweeping the skies to see if there's any radio signal from ET coming our way. But so far, only an eerie silence and no money. So this is the way forward lies either with getting more money or with thinking a bit outside the box on how we might detect signatures of intelligent life beyond Earth. But I'd like to draw this to a conclusion by a quotation from Frank Drake, who started the subject of SETI in 1960. So that's 45 5 years ago. This was an incredible gamble. When Frank Drake did it, people thought he was totally crazy. As I've explained at that time, nobody really believed there was any life beyond Earth. And Frank has been persistently looking for this. And I have to admire his staying power. Who else do you know has designed an experiment, run it for 45 years, got a null result, and still remains upbeat about the future? But Frank is convinced that we're going to discover intelligent life beyond Earth very soon, and I hope he's right. But at this stage, we cannot give the betting odds. But I will finish because I think he describes so well why everybody cares about the subject of life's origin and are we alone. They care because it touches upon what we human beings are and how we fit into the universe. So Frank says that SETI is a search for ourselves, who we are, and where we fit into the universe. So ladies and gentlemen, thank you very much.